It's a great pleasure to be here today, so thanks very much for inviting me. I'm looking forward to talk to you about pervasive and sustainable AI with adaptive computing architectures. But before we get to the fun technology, I'm going to spend 1 minute to give you a little bit of background about me and my team, so you have a little bit of an understanding about who we are and where we come from and what we do. So we work in AMD Research, which is a global organization, about 150 people worldwide. My team is the Integrated Communications and AI Lab. There's about 20 researchers in it, top-class PhDs from all over the world. We're spread over 5 locations, from San Jose to Europe, including Ireland, where I'm based, all the way down to Singapore. And fun fact, so we were originally Xilinx Research, which got then, of course, acquired by AMD in February last year. So topic-wise, the focus is on AI and communications and everything at its intersection, whereby we're doing a really hands-on approach to research, so it's we're writing papers as well, but it's much more building full systems, doing architectural optimizations, optimizing algorithms, and benchmarking to keep ourselves honest, so the whole spectrum. Okay, I also like to take the opportunity to shamelessly advertise our internship program. So we have on average about 10 interns spread across the various locations. I want to say there's over 100 interns that have meanwhile come through my lab. And they're actually a fantastic opportunity for collaborations. And I mean that not only in the sense for collaborations with universities, but also in the sense of collaborating with industries. Okay, so that's as much I wanted to say about the background. Let's dive into the crazy world of AI, and I'll just ease us slowly into the topic with an intro slide. So AI is huge, right? There's tremendous potential that comes with deep neural networks in particular. And in my head, there's really 3 reasons that drive this. The first one is that neural networks require little domain expertise to solve problems. And what that means, said very casually, is that you can actually use neural networks to solve problems you don't fully understand, right? So that's a big deal. The second part is that neural networks have the mathematical property of being a universal approximation function, which means the scope of the problems that you can solve with it is vast, right? And the third reason is if you make your neural network big enough and you train it hard enough, it can outperform humans as well as existing algorithms on specific tasks. And that mixture makes it extremely powerful, and because of it, it is increasingly used to replace existing algorithms, not always, but it's happening, and in addition to solve previously unsolved problems. And that's really the big deal here, right? To give you a few examples, I mean, you would have to live in a cave not to have heard about this, right? But we have code generation with GitHub Copilot. We have text generation with ChatGPT. By the way, ChatGPT is also amazingly good at writing malware. Image generation with Stable Diffusion, and GPT-4 even now passes the bar exam, right? And not just on average, but in the 90th percentile, right? So, and you could say, well, these things are kind of perhaps a little bit more gimmicky. The big deal that's really happening is the scientific advancements. And for me, like the number one thing is probably Google DeepMind's AlphaFold for predicting 3D structures of protein, and that has advanced so much that today they can predict with AlphaFold almost every 3D structure of protein known to science. And that's, of course, so important for drug discovery, for cancer cures, and God knows what will come from this. So this is super important, and because of this, we see increasing adoption of AI from cloud to edge and everything in between. So AI becomes pervasive. And all the hype is in the data centers, right? Everyone talks about ChatGPT and recommenders and web search. But this talk is about the whole spectrum of AI applications, about this long tail of applications, AI being used in communications, in medical, in IoT, in sensor intelligence, everywhere. And as you can imagine, as you deploy AI in these truly different scenarios, that comes with very different requirements. So it's really different and truly diverse requirements you encounter. So first of all, when you start off with power, like if you look at the power envelope that we have, let's say, within a hearing aid for noise filtering, compare that to a GPU accelerator card sitting in a data center training a large language model, right? Very different envelopes. Very different requirements with regards to performance in terms of throughput, latency, and jitter. You have different requirements with regards to cost, and of course, everyone cares about cost. But there's different price brackets again, right? Real estate, how much space do you have for your chip? Accuracy. A security application would have sky-high accuracy requirements. Compare this to a recommender which suggests the next Netflix movie that you're going to watch on Saturday night. So it's a big spectrum. Different I/O requirements depending on which sensors you integrate with what network interfaces you have, and then of course different temperature ranges and functional safety for automotive and aerospace and defense deployments. To make it a bit more concrete, I'm showing here very specific requirements that we got from customer engagements. To start off with, in the embedded space, and you probably don't find this surprising at all, right? In the embedded space, the customer cared about a small resource footprint, low power, below 10 watts we talked about here, low latency, below 1 millisecond, and zero jitter. High frequency trading is also a really popular space now for neural networks. You might be well familiar with it, but just to make sure everyone's got it covered, it's an arms race of acquiring data and making trading decisions. And supposedly, every nanosecond accounts for multi-million dollars. So I actually want to charge a commission for the nanoseconds that I save people in deployment of neural networks. So I'd be retired by now, probably. So the DNNs are actually being deployed as part of the trading decision. And therefore, the neural network has to execute with nanosecond latency, right, again. So this is very extreme. Similarly enough is actually particle physics, right? We might even have people from CERN here today, right? So the CERN, the Europe's largest hadron collider, right? They also care about nanosecond inference time. Why is that? Because they're generating a humongous amount of data. They're generating on their collider, when they do the measurements, 7 terabit per second amount of data, right? And it's a needle in the haystack game, right? Because you want to discover, of course, the next Higgs boson or whatever is coming after it, right? But you can't record, the all data that comes in at 7 terabits per second. So what they do is they take neural networks for the trigger condition of what data to record. So that's, again, nanoseconds, because you're accumulating very fast at 7 terabit per second. Yeah, and then communications, and I made a whole slide about communications because AI is taking off big time in the communication space. Now, there's still extreme throughput requirements in the comm space. Now, it's compared to CERN, right? Particle physics, it's lower. Now, we're talking only a few hundred gigabit per second when working on Ethernet traffic. But that's still a tremendous throughput, right? And especially if you accumulate, let's say, if you operate on 64-byte packets in the worst case, that will translate to hundreds of millions of inference per second that you have to execute, which is way beyond, for example, what you do in data centers, right? So extreme throughput requirements, and again, many of these are latency sensitive. So for example, you have in 5G and 6G wireless, you have real-time constraints for end-to-end communication. It has to be within a millisecond. So that dictates, when there's neural networks deployed on the communication path, that it has to be well below this. And because of that, you can, for example, not afford to have a runtime overhead for your accelerator. You can't take the data in from your network and then call a neural network accelerator, because that already introduces too much latency. So you need direct streaming integration of the neural network accelerator with your network interface. And then the latest thing that we're seeing now, that there's a fusing of standard signal processing functionality with neural networks. So this is from a paper from Nokia Bell Labs, the DeepRX paper, which shows that they use 4 neural networks in a combination with a DSP block. So it becomes much more complex, the compute that you have to deal with. So upshot from this slide, DNNs are making big inroads in the communication space, right, from traffic monitoring to prediction to optimization, even deployment within physical interfaces. And it's paired with extreme throughput and ultra-low latency requirements. So we have a lot of diverse requirements, and this whole thing is now paired that everything is in flux. Everything is dynamic, right? Why is that? Because AI is a research topic. So the algorithms haven't matured yet, and they're still changing all the time, right? So, for example, there's this epic discussion about data types, right? What's the right data type for neural networks? Started off 32-bit floating point, then we went to 8-bit fixed point integer. Now we're meandered all the way to 8-bit floating point. What's next, right? Is it logarithmic number systems? And these are big deals, right? When you're building hardware, you need to know, what's your operator. What's the next operator that will dominate the compute paradigm? I mean, transformers only arrived in 2017, that's 6 years ago, and they're absolutely everywhere. So there might be something new coming down next month, right? And we can forget about all the great hardware we've built and start from scratch again. And what's the next generative paradigm? There were originally the variational autoencoders, then we had generative adversarial neural networks, and now we're going to denoising diffusion. What's next, right? Nobody knows. And then you have really disruptive stories like Jeffrey Hinton, one of the AI celebrities, his keynote at NeurIPS last year, who says, we're no longer doing training with stochastic gradient descent-based backpropagation, we're going to do now forward, right? it's fundamentally different to everything we've done before. So, and then on top of that, and that's perhaps less esoteric, is customer workloads are changing, right? I mean, the hardware engineer might be working on the accelerator, and then the data scientist in the other department actually figured out if he changes one of the compute operators, the neural network will have much better accuracy. So the workload is always in flux. So we talked about pervasive AI coming with diverse and dynamic requirements, right? Now, in parallel to this, we have to talk about energy consumption. And the example I give here is now from the data center, and that's of course because in the data center the numbers add up much better, right? And they really stress the point. But this is true everywhere, right? So here's power consumption for ChatGPT and for a Meta AI cluster. And there is a lot of variation depending on what news article you read or where you get your measurements from. But order of magnitude, we're in the right ballpark here. So ChatGPT running on 100 GPUs, I believe it was, 4.3 gigawatt hours, right? And the Meta AI cluster is between somewhere around 50 terawatt hours today, and expected to exceed 500 terawatt hours in the future. Right? What does that mean? How big is this? Well, that's on par with the energy footprint of an industrial nation, right? So I have Ireland here because I live there, right? We have 20 terawatt hours, and Germany is over 500 terawatt hours in that was 2022. But this is kind of the order of magnitude that we're talking. And it's pretty insane. It's actually scary if you think on how much energy we're burning on training large language models. Why is it so brutal? Because honestly, if you look at the algorithms, it's a sledgehammer approach. I mean, we're using terabytes of data, running matrix multiply across hundreds of servers, and just sloshing the data back and forth. It's extremely inefficient, and you compare that with the human brain. 20 watts up there, right? And definitely not matrix multiply going on in there. Not quite sure what's happening in there, not matrix multiply, right? So there's orders of magnitude that we can do better. So I'm convinced the paradigm will shift. It has to shift, and it will shift. And you can already see the trends picking up from Google Trends here. Right? You see the nice curve. So you could say that in the past, up to 2012, it was all about getting neural networks to actually work. Then we spent 10 years on actually scaling it up and scaling it out. I think the next decade is all going to be about energy efficiency, and maybe even longer than that. Who knows how long it's taking us to figure this one out. Anyway, what's the industry doing about this? Well, the number one trick in the book, that's what everyone is doing as we're approaching end of Moore's law, is specialization of compute architectures. And everyone's doing this, right? We have Google's TPU, Huawei's Ascend processor, AWS has Inferentia, everyone builds their highly customized silicon. Then you have all the startups from Grok to Cerebras, and even in the automotive space, you have Tesla building their own AI ASICs. And AMD is doing that, of course, as well. The challenge with it is that specialization of your solution takes a long time, right? So we're talking probably somewhere, roughly speaking, between 18 and 36 months, right? You go through your classic waterfall diagram with application analysis, architectural specification, RTL design test, physical design, software, by the way, not to be underestimated. This is typically half of the time is spent on the software stack and followed by test and maintenance. So it takes a long time. And the challenge is you don't have that time, right? Because you have these dynamic requirements. Just to illustrate the point, let's say you build an accelerator for image classification starting off with ResNet 50, 8-bit fixed point integer representation. You're halfway in the RTL design, and in comes your data scientist and said, no, we have something much better. We're doing vision transformers with FP8 now. And you're back to square one, right? So the development time is far too big in comparison to the available time that you have. So what we really need here, this kind of summarizing it up, is agility in the customization process. So you have dynamic and diverse on one side, which means you need agility and fast turnaround times, and on the other hand, you have this need for customization so you can actually get sustainability, energy efficiency, and that's at odds with each other. So what we advocate and what our work is all about is enabling rapid specialization with adaptive compute fabrics and agile AI stacks. So we propose this three-layered approach, which consists at the bottom of the stack, adaptive compute fabrics, which allow you to post-silicon adapt your compute architectures to the specifics of your use case so you can actually achieve high energy efficiency. Then all the tricks in the book to actually customize the hardware architecture, and on the top of that you have the AI stack. And I'll take you now through these three layers step by step, and we'll start at the bottom with the adaptive compute fabrics. So what are those? Well, that's actually the new code word for FPGAs and AI engines. I'd say most of you are probably well familiar with this already, but just to make sure that I'm not leaving anyone behind, very quickly, primer, FPGAs are the chameleon amongst the semiconductors because they give you the flexibility to adapt your hardware architecture post-production, right? You can customize the I/O interfaces, you can customize the functionality, you can make it a compressor, an encryptor, a key value store, a neural network accelerator, whatever you like. And you can customize the compute architecture to fit a certain performance or energy target. And that's, of course, what we're doing here. Physically, structurally, they consist of a sea of lookup tables. LUTs for short, there's about millions of those in the latest devices. They have a programmable interconnect in between. They have programmable I/O. They are interspersed with DSP elements, which do n-bit multiply and accumulates. And they're interspersed with a lot of embedded memory. So you would have hundreds of megabytes with humongous access bandwidth. So key on this slide here is that the FPGAs are flexible and provide you the ability to customize the hardware architecture post-production. So that's the important bit here. The newer evolution of FPGAs are the AI engines. I'm just going to touch super briefly on this. They are more specialized, higher performance. They consist a sea of vector processors rather than lookup tables. So a little bit coarser granularity. Because of that, they get higher performance. And if you compare it to the FPGA is bit level granularity. AI engines is word level operators, right? They consist out of up to, I think the largest device has 800 AI cores. These are VLI-W CMD processors, by the way. Still have a flexible interconnect in between, also each of the cores, separate control flow, tightly integrated memory, and compared to the FPGA, they're actually software programmable, so they're no longer time enclosure. For those of you who are working with FPGAs, that's the good news. Anyway, this talk is foremost about FPGAs, because FPGAs have that phenomenal advantage that they are already diverse. To give you a feel for it, we have over 100 product families, right? So spanning silicon nodes from 350 nanometers all the way down to 7 nanometers. There is another fun fact, 500 plus base parts, right? That is actually different fabric sizes, different mixture between DSPs and lookup tables, and some with HBM, some with ARM cores, some with analog to digital converters, etc. So you get different mixtures, 3 different temperature grades, 3 different speed grades, and then you have red hard versions and stuff like that. Point here is really they are already incredibly diverse, and there is a fair chance that whatever your needs are, you actually find the device in the right size. So we covered the base layer, which were the FPGAs, right, which give you the flexibility to customize the hardware architecture in order to get energy efficiency. Let's talk now about how we can customize the hardware architecture to get there. And there's 3 tricks in the book. And I also want to stress here the fact that you could apply all of these tricks, of course, also when you spin your ASIC or you create your own accelerators. The beauty here is that you can actually customize to specific use cases. You can afford a much higher degree of customization because you can always reprogram the FPGA, reconfigure it to run a different neural network. Right? So the first trick is custom data flow, where I customize the accelerator to specifics of a topology. Second one is quantization, super popular on quantizing all the operators to specific representations. And the last one is sparsity, where I customize my accelerator for leveraging to avoid multiplications with zeros, so to speak. Let's start off with custom data flow. So the idea with custom data flow is that I create an accelerator for a specific neural network. For example, a ResNet 50 accelerator. And the way I do this is by actually recreating the neural network inside the hardware, right? So every layer is represented inside the FPGA, whereby I give proportionally compute resources to the compute requirements in each of the layers. So if the first layer takes 10x the compute to the second one, it gets 10x the compute resources in the FPGA. And out comes from this a balanced data flow implementation where I can just stream the inputs through the neural network. So it's very different. Your standard accelerator would be, you schedule the layer, the compute of one layer onto your accelerator, then schedule the next, then the next. So this is a pipeline implementation, so to speak. And then, by the way, my cats and dogs kind of stream through the accelerator. So you customize everything to the specifics of your application, and the benefit that you get from this is, of course, energy efficiency. I only create what I need. Latency, because I'm not buffering in between the layers, everything just streams through. And thirdly, the ability to scale throughput hardware resources. And I'll touch briefly on those in more detail. So this is when we go a little bit more technical. Let's talk about energy efficiency benefits that I get from data flow. Well, the first one is, as I just said, because I only create the hardware that I need. So I have exactly the memory footprint that I need. I only instantiate the compute operators that are in my neural network. If I don't have a square root, I don't create it in the hardware. So that gives you better energy efficiency. The second one is it minimized the movement and storing of data, and that's actually a really big deal. So because I stream the data from one layer to the next, I don't have to do this intermediate buffering in between the layers. And that intermediate buffering is super expensive. Now, Matthias could tell you a little bit about memory consumption in DRAMs, right? But this is like, we're talking here 1,000 picojoules in the 7 nanometer fabric for doing a DRAM access, compared to like somewhere between 0 and 1 or 2 picojoules for an arithmetic operation. So memory is avoided. Big deal, right? And the third one is, because it's not buffering, the execution time is shorter. And energy is power consumption multiplied by execution time. So if I'm faster, my energy consumption will go down. Okay, so the second benefit of data flow is that I can scale it from small to large, from mouse to elephant. So I can let it address different points within the design space. So let's say I have a 4-layer neural network and I have a tiny device here, let's say 1,000 lookup tables. I can create that neural network with a very small footprint. Each layer again is represented, whereby I give it proportionally compute resources according to the compute requirements within the neural network. Now, if I have more resources and I need higher performance, then I can just proportionally scale each of the layers out. Again, balanced data flow gives me a higher performance envelope. And I can keep playing that game until, let's say, in the extreme case, where every neuron and synapse in the neural network has a dedicated hardware resource, right? And when I have that, if it's like a one-to-one mapping between the neural network and the hardware, I can classify clock rate. So that means if I clock my circuit at 400 megahertz, it will run inferences at 400 million inference per second, right? So one neural network executed every clock cycle, right? And that's extremely fast, and that's what gets you to the requirements in the communication space. So how do we do this? How do we actually implement this? We do this through a parameterizable kernel library. So each kernel represents a layer in the neural network, whereby I can parameterize each of the instances with regards to the degree of parallelism. And that allows me to scale it up and down, basically. So I can, for example, say how many inputs do I want to process in parallel. So first, the degree of parallelism. Second, I can parameterize it in the data types that it operates on. And to some degree, I can parameterize the behavior, so what type of activation function, for example, you want to use. Each of the kernels comes with axis stream, so data streaming inputs and streaming data outputs, which makes it super easy for accelerating assembling a whole neural network. And everything is written in C++. This is synthesizable code, and we run this then through our high-level synthesis tool and the backend flows to generate the hardware design. So that's roughly speaking on how we can generate these parameterizable data flow architectures. So that's the first concept. The second trick in the book is the quantization. So what's the minimum representation of the parameters and all the variables in my neural network that I can get away with while still achieving the accuracy? Everyone plays this game, right? ARM does it, I'm sure NXP does it, everyone does it, right? Now the beauty is with the FPGA, again, I can play this game a little bit more than others, right? I can literally quantize to each layer can have a different data type representation, and I can mix and match them across to whatever is needed. Why is this such a big deal? I mean, this is literally the #1 trick to resource savings and performance scalability. I mean, we've actually benchmarked this right on the FPGA. What's the compute resources for n bit multiply accumulate? And you can see it, like between a 1-bit multiply accumulate and an 8-bit is 70x difference with regards to how many lookup tables it consumes. So it's massive, right? So if I can shrink down to 1 bit from 8-bit, I can either shrink my hardware resource by 70x, which is a big deal, or I can instantiate it 70x times, which gives me, because neural networks are so parallel, a performance scalability of 70x. There's huge benefit in there. And then, of course, it comes with energy savings. So back again to my favorite table. This is for 7 nanometer fabric. So first of all, if I use it for performance scalability, my execution time shrinks, and because energy is power times execution time, it will become more efficient. Secondly, reduced precision operators are inherently more efficient. And again, like here you can see the energy per operator for multiply and addition separately for 32-bit, floating point, and fixed point, and 8-bit as well. And there's order of magnitude in between, right? So this is a big deal for energy, and then of course because you shrink inherently your memory footprint, it reduces memory access, and we talked already about how expensive DRAM accesses are. Okay, so that's quantization. Last trick in the book is sparsity. So neural networks are naturally sparse. There's lots of zeros in there, and I don't want to multiply with 0 or read zeros from memory if I can avoid it. Actually, if you compare it to the human brain is, would you believe it, 98% sparse, and I am convinced early in the morning I might be even sparser than that. The challenge with sparsity is that it leads to irregular compute patterns, right? And when you operate with vector or matrix-based execution units, you're going to be very poor efficiently, right? So it's very hard to parallelize this. However, with the data flow, coming back to it, right, when you can actually replicate your neural network in the hardware, you can replicate any irregular compute graph. So you can maximally exploit the sparsity. And we actually drive this even a step further in our research project, LogicNet. There, the idea was that actually, if you take a lookup table in your FPGA with 6 binary inputs and a binary output, that is actually a neuron. That is equivalent to a neuron with 6 inputs, batch norm, floating point weights, and a binary output. And by the way, we can scale this to more inputs and more outputs, but just to get the basic idea across. So that's actually equivalent. And what you can do is then you can turn the whole problem on its head, right? So up until, like, what everyone is doing is you train a neural network, you optimize it for your hardware, and then you deploy it. What we do now is we say, oh, we pick a great circuit in an FPGA. We create a circuit, and we say, that is my neural network. And then we represent that circuit in our training framework and let it learn a new machine learning task. And if we get accuracy, what we get out of this is maximum performance by design, right? And you might wonder, is like, between these highly quantized data flow implementation and this, is there much to gain still? There's a huge amount to gain. And I'll show you in the results section on how much additional benefit you can get from this extreme co-design of what we're doing here. Okay, so we talked about the lower 2 layers, about the adaptive compute fabrics, the customized compute architectures. Now let's talk about how can we automate this specialization process, because there's not enough hardware engineers on this planet, right? We need to make it easy, and we need to make it fast, and we need to make it agile. So how can we get away from this, right, from this big water flow diagram to the right-hand side? And the good news is the FPGA already helps, kind of takes away the whole physical design process, and the parameterizable data flow architecture takes a lot out of the architectural specification and the RTL. So you have now an incremental process here only, right? So now we need to pair this with a graph compiler and with an agile quantization library, just to make this easier. So what I give you is not a magic wand, but I give you an end-to-end flow, which helps you with this. And it's what we do in our projects, Finn and Brevet does. So they let you get from all the way from a DNN all the way down into a bit stream. And it enables the generation of these highly customized architectures using all tricks in the book, using data flow, reduced precision, and sparsity. So key components here are Previtas, which is the training library. then the Fin compiler, which generates the hardware, and the kernel library that we discussed already before. And also really important here is everything is done open source. And that's so important because it makes it way easier to collaborate, it enables third-party contribution, and it allows people to customize and fine-tune it to their own requirements. So I'll walk you now through the stack from top to bottom. So we'll start off with Gravitas, which offers you, I call it agile quantization support. If you have a better name, let me know, but the key idea is it has first-class support for custom data types. So arbitrary precision, fixed point, floating point with block scaling is supported in the library. And if you come up with the next best numerical representation, we can represent it here. Second part to this is it's composable, right? So you can define different data types, different quantization techniques. Maybe you want to do something uniform or non-uniform, and different training paradigms, being it quantization-aware training or calibration-based or direct quantization, and you can mix and match these different combinations here. And it integrates with different compiler stacks. So it outputs an Onyx description, which is a standard representation, and feeds into all the various AMD flows, including Fin, of course, but also miGraphX, which is the compiler stack for the GPU, as well as SenDNN, which is the compiler stack for the CPUs. So out from Gravitas, we ingest the representation in the Fin compiler. Now, the Fin compiler is a modular graph compiler with well-defined abstraction levels. What it does, that it incrementally lowers the Onyx description all the way to a hardware description through graph transformations. It performs all the optimizations, including layer fusion. It allows you to explore the design space. What's your performance and your resource target, and the compiler can then scale it up or down. And it code-generates the C++ description. Those are now basically instantiations of the kernel library template classes. From this, you go through the backend flow, and it generates you an IPI design. For those of you who work with Vitus, they might recognize this. And this is, by the way, it's as simple as this. There's a 4-layer neural network. Each of them has 3 inputs, which is clock reset, of course, plus the data stream in, where the data from the previous layer comes in, and then you have the data stream going out. Okay, so that's the Fin compiler. So let me show you some example results of what we have achieved. So this is benchmarking exercise. So we said, let's not care about accuracy for a moment. Let's just look at the energy potential that I get from quantization and pruning. What can I achieve here? So we've benchmarked 2 different neural networks, a multi-layer perceptron on the left-hand side and a convolutional neural network on the right-hand side. Now this is fairly packed charts, so let me explain you these box and biscuit charts. So overall, I'm showing performance over power in this chart, right? So you want to be high as possible for efficiency. Each of these boxes represent is a summary of measurements over different stream sizes. You have 2 groups. The group on the left is the 4-bit integer representation. The group on the right is 2-bit integer representation. And then with each of the groups, I have different degrees of sparsity. So the smallest efficiency is the 100% neural network. Then the next one is pruned to 50% of its connectivity. Then the next one is pruned to 25%, and then the last one is down to 12.5%. So what do we get? From quantization, there's 3.4x and 5.5x benefits to be had from quantization. And from pruning, it's even bigger, right? There is a real big deal from 49x to 74x for the convolutional neural network. Now, you might say, well, that's kind of obvious, right? That's kind of what I expected. What do you actually gain from data flow? Now, that's a little bit trickier to measure, so here's what we've done. So we've taken a generic neural network accelerator and implemented it on the same FPGA, so same device, same platform, and then we took the same one and created from that a 2-bit data flow accelerator. And this here shows energy per inference. So that's over 1200x more efficient. Right? It's an insane number, and you're going to get from the quantization, you get something like 30 to 40x, but the other 30 to 40x actually coming from the data flow, by not going to the memory. This is the big deal. Now, the next question is, if I go now to logic nets, do I get any more? Because 2-bit data flow accelerators is already so optimized. Is there more to be had from this? And there is. There's a huge amount to be had. There's another 3.6x when we went to logic nets, right? I actually had to zoom this up. And if you combine this, now this is an insane number, 4,500x energy improvements. And you could say, maybe she didn't pick a good baseline, right? Now, of course, I give you that, right? But the key fact here is there's a huge amount of energy savings, and I would encourage everyone who's deploying neural networks and hardware to take a hard look at it. We didn't have a single customer engagement yet where we didn't get orders of magnitude in improvement in performance acceleration and energy savings out of it. There's so much redundancy in these neural networks. Okay, so let's go more specific examples. This is a cybersecurity example. Now, I'm not sure how familiar you are with the space, but there's cybercrime is massively on the rise because ChatGPT is writing great malware, and every script kiddie can now be a hacker. You don't have to be an evil super genius anymore. Every script kiddie can do it now. So because of that, cybercrime is on the rise, and guess what? Machine learning is also really good at security. So people throw machine learning algorithms into the next generation firewalls. And the challenge here is that firewalls need to chew up an awful lot of traffic. So now you have, coming back to the communications requirement, extreme high inference per second requirements plus low latency. So here's a very simplified yet typical block diagram of a machine learning-based traffic classifier. You have network interface on ingress and egress, packet processing, which extracts, for example, 5-tuple and flow statistics, feeds into your classifier, which decides whether it's good or bad, and then you either drop or pass, and out goes it back on the network. So we've implemented two variants. The first one is a thin implementation of the UNSW dataset malware classifier. We've quantized it down to 2-bit activations and weights with equivalent to floating point accuracy. This runs 300 million inference per second. So this is one of those classifying at clock rate, and it fits into 8,000 lookup tables, which is tiny, right? The new devices have millions of them, and it has 18 nanosecond latency. So this is how fast and how small it can go. We have a second one. This is still work in process. This is a DDoS classifier on an open source data set. Again, quantized it down to 2-bit weights and activations with adequate accuracy. It's currently at 19 million inferences per second and 18,000 lookup tables. And there's no reason why we won't get this one to run as fast as the first one. So we're going to scale this up, but we're still going through some iterations. So this is cybersecurity. Another one in the networking space is modulation classification. So this is the problem as a key enabler for software-defined radio. You want to understand what modulation schemes are being used in your spectrum, for example, for spectrum interference monitoring and dynamic spectrum access. The challenge here is, again, throughput, right? So you need to basically process gigahertz sampling, which leads to millions of inference per second. So there's a lot of data points, but let me make it simple. So you have on the y-axis throughput, and as I just said, you want to process gigasamples per second in your radio spectrum. That's a logarithmic axis, by the way. The x-axis is latency, right? So you want to be as far to the left as possible. Whenever you deploy this as part of a control loop, latency is critical. So you want to be left and high up. So on the right-hand side, from your view, those hockey sticks are the GPU measurements. And this is typical GPU behavior, right? So it shows the number of measurements over batch size, which is the number of inputs I process in parallel. I have a server class GPU here and two embedded GPUs. Let's just look at the server class. So if I just process one sample at a time, I get this point down here, right? This will have the lowest latency of all the measurements, but low performance. I'm nowhere close to the gigahertz sampling rate that I want. In order to get there, I have to process at least 256 samples at the same time. But that comes at the cost of latency, because now I have to accumulate 256 inputs before I process them in one go. So I get high throughput, but at the cost of latency. So this gives me orders of magnitude of latency penalty. Whereas the data flow implementation will sit up here, right? So this is an embedded platform on an FPGA, gives you the gigahertz sampling, and it's 1.7 gigasamples per second with 2 microseconds latency. So that's the difference here. Another example, and this is how tiny can you go? How small can a neural network get? This is an example from CERN, jet substructure classification problem. This is a 16 input, 5 output classification problem. Now, this is not great accuracy, but it's a working classifier with 70% accuracy. That fits into 30 lookup tables. That's like it's smaller than a 32-bit adder. And it classifies over 600 million inference per second, 3 nanosecond latency. So this is how tiny and fast they can go. And if you can have these small accelerators, you can deploy it absolutely everywhere, right? Another example from Logic Nerds, and excuse the lack of modesty on this side, but this is a great story. So, and this is a much less esoteric example than particle physics, right? This is Menis digit classification problem, really classic machine learning problem that everyone does, and it makes it great for comparisons. So at NeurIPS last year, right, #1 machine learning conference, Peterson et al. Wrote, and we were delighted with this, that Fin is actually the fastest Menis classifier that there is at 98.4% accuracy. To give you the data points, here I have 2 different accuracy targets. They're between 83,000 and 91,000 lookup tables. Latency is over 2 microseconds and 300 microseconds, and it's around 1 in 12 million inference per second. So this is a binarized neural network with a data flow accelerator. And you think, this is already like super optimized. I mean, can we still squeeze something out? And we did. And this is the Logic Nets implementation. So this is again where we picked the circuit and let it learn the problem. And you know what? So we got another up to 300x for the higher accuracy target out of this. And we shrunk the latency down into the nanosecond range, and we have the footprint, right? There's so much redundancy in these neural networks, and if you put a bit of effort into this, you can really optimize to a large degree. Okay, so we have, this is well beyond research, this project now, right? We're running with this already 6 years, and we're building up professional customer support with AMD's CSE organization. So if this is something of interest, this is well matured and in transit now with the technology transfer. We worked in applications in communications, in medical, in sensor intelligence, automotive, the particle physics, cybersecurity, aerospace, defense, and high-frequency trading. And our open source project is getting a lot of traction too. Like Brevitas has over 200,000 downloads, QOnix has over 72,000 downloads, so it's well taken off. And we also have some good academic results, our best paper awards, and over 1,000 citations, which we're fierce proud of. Yeah, and that brings me to the end. So we talked about pervasive AI with this long tail of applications having truly dynamic and diverse requirements. We covered also that in parallel to this, we need to have this paradigm shift. We have to start paying attention to energy efficiency. I advocated that enabling rapid specialization with this 3-layered approach of adaptive compute fabrics, highly customized execution architectures, and agile AI stacks, that is the solution for what we need. The adaptive computing platforms already are available with the great diversity and with the highly customized compute architectures. we can really get you energy efficiency. We can really bring you orders of magnitude improvement using data flow, shrinking precision, and fine granular sparsity. I didn't give you a magic wand, but I gave you Fin and Brevitas as a way to speed up the automation through a graph compiler and a quantization training library that gets you from DNN all the way to the bit stream. And I hope that the proof points that I showed you in the results section convinced you of the potential that there is there. And maybe Fin and Brevitas is not for you, but I hope that at minimum what you take away from this talk is that you should take a second look at the deployment of your neural networks and consider that there's orders of magnitude in energy savings that you can still achieve. If this is of interest, let me know. We'd love to hear from you and work with you on this. So just to flash this up, in case you want to go experimenting, we have some great resources made available for free. There's one is the HAC, the Heterogeneous Adaptive Compute Clusters, which give you free bare metal access to the latest adaptive computing devices. It comes with a whole community. There's hundreds of institutions working on these. There's 5 centers, by the way, worldwide. And they share all their work through open source repositories. So if you want to get started, there's a lot of resources and community in these ones. And the second one is the HPC Fund. This was created during COVID times. It's all about accelerating science in the public interest. For example, COVID vaccines were researched with this. It comes with a lot of training sessions. These are CPUs and GPU clusters from AMD freely available for these type of purposes. Again, also good networking with peers. So if any of this is of interest, check out the links. We're going to share the slides anyhow. And with that, thank you so much for your attention. It's been a pleasure talking to you. More than happy to answer some questions.